Hey guys, this is 7-5 parts of similar triangles. We are going to learn about the special segments that exist in a triangle and how they relate to each other when you have two similar triangles. So the first one, Theorem 7.8, and all these go together. These theorems, 7.8 through 10, are all about special segments of similar triangles. So if two triangles are similar, so you know that they are similar, the lengths of the corresponding altitudes, remember we did altitudes, are proportional to the lengths of the corresponding sides. So that means the ratio of the altitudes, so AD to FJ, is the same as the ratio of the corresponding side lengths. So that means that if we're given the triangles are similar, like ABC and FGH, we know AB is to FG as BC is to GH and CA is to HF because we know the ratio of the corresponding side lengths form a proportion. Well, not only that, now we can tack on to the end here equals the ratio of the altitudes. So AD is to FJ. They all form a proportion. So that means we can take the ratio of any pair of corresponding side lengths and set it equal to the ratio of the altitudes and use that to solve problems. So hypothesis, that's given two triangles are similar. You have to know they're similar. Conclusion, then their corresponding altitudes are proportional to the corresponding sides. And really should say to the lengths of the corresponding sides. All right, so if triangle ABC is similar to triangle FGH, we have our conclusion is that long extended ratio or proportion that I had up there. And I'm going to write the AD part first. So we're going to say, just because that's the part we're focusing on, that's the new part, that the ratio of the altitudes, the lengths of the altitude, so AD is to FJ, as AB is to FG, as BC is to GH, as CA is to HF. All right, so that's the first theorem. And then we've got another, we have an abbreviation here actually. So like in a proof, you would have to say this for your abbreviation. So you would say similar triangles have corresponding altitudes proportional to corresponding sides. I know it's a lot, but it's still a little shorter than all of that. So that's what you would give as your reasoning. So if I ask you for a reason just to say, hey, how are you able to solve this problem like I do, that would be a reason. Okay, so now it turns out that not only does that work for altitudes, it also works for, what are these things right here? Angle bisectors. So each triangle has 3 of them. We're just going to talk about one of them at a time, but the proportion we're going to set up would work for the angle bisector of any of these 3 angles. So it has to be the corresponding angle, right? It can't be the angle bisector of K and then the angle bisector of R, but K and R don't correspond. It's corresponding angle bisectors. All right, so if 2 triangles are similar, the lengths of the, again, corresponding angle bisectors, that means they have to actually happen at the same vertex, are proportional to the lengths of the corresponding sides. So I just put that little note there, and that's the same idea up here also. I didn't say, but like if A and F were not corresponding, then it's not going to be proportional. It has to be from corresponding altitudes. Corresponding, that's the key word there. It has to come from the same vertex. Again, since there's 3 altitudes in a triangle also. All right, so our hypothesis, 2 triangles are similar, then their corresponding angle bisectors are proportional to corresponding sides. So we're going to have the exact same thing as above, just with some different letters here. So if we were given that triangle KLM is similar to triangle QRS, then we know the ratio of the angle bisectors, which we're doing just one pair of them, but there are 3. LP is to RT, as KL is to QR, as LM is to RS, as MK is to SQ. So remember, with similar triangles before, we knew this piece. We've always known this piece. We're tacking on another one. So say if we had another point here that was, say, x, and this one was y, ky and qx would also be ky is to qx, would also work if it was an angle bisector. So if that segment I was talking about was an angle bisector, that would also work here. So whatever angle bisector it is, and even angle bisector to angle bisector would work, because if this angle bisector, if LP is to RT as all of this, and then say we have another angle bisector here, I draw on another one and say, oh, we've got this other angle bisector, and like I said, that's K or Y, and then, oh, look, another angle bisector. I told you we can put either of them in here. So that means that it would tack on the side so that LP is to RT as KY is to QX. So within the triangle, all the three angle bisectors are going to be the ratio of the corresponding angle bisectors. All three of them are all equal as well, because they're all equal to the original proportion that we know from similar triangles. I'm not sure that that ever really pops up, but just wanted to let you know. All right, so we do have an abbreviation for this one as well, so it's going to be similar to the last one. So similar triangles have corresponding angle bisectors proportional to corresponding sides. So not too hard to remember. And you can always write it out in words, right? All right, we have yet another one, because remember, we talked about altitudes. The point of concurrency for them was the orthocenter, which was useless. And then we had the point of concurrency for the angle bisectors was the what? Incenter. And then we had, of course, the intersection of the three medians, which was the centroid. And the only one we don't have here is perpendicular bisectors, which would have been the point of concurrency was the circumcenter. All right, so if two triangles are similar, then the lengths of the corresponding medians, so let's review what medians are. They start at one vertex, and the other endpoint of the segment is the midpoint of the side opposite. So that's why these are marked as equal in measure. And really, I believe I should have done this between the two figures. I mean, they're really separate figures, but because they're all together, it really should have been a double hash mark there, really, because these aren't all necessarily four congruent. Anyway, so the medians are proportional to the lengths of the corresponding sides. So that's our hypothesis if the triangles are similar. So if triangle ABC is similar to triangle WXY, then we had all those proportions that we had before, but that the medians join in there. So I'm going to say DC is to ZY as AB is to WX, as BC is to XY, as CA is to YW. And again, just like the other ones, there are three medians in a triangle, so those would also join in here. So if we had B whatever X here, and then we had, oh, well, I don't want to use X, BM, and then we had XN here, then those would also form a proportion, not only with all these guys, but with this other ratio of the proportions, or the ratios of the corresponding medians. So the abbreviation is going to be the exact same. Similar triangles have corresponding medians proportional to corresponding sides. So these are all theorems, but I'm never going to ask for the theorem number, right? You're just going to explain that, oh, well, the corresponding ratio of the corresponding medians, that's proportional to the ratio of the corresponding side lengths. You know, that's what you're just going to explain. And so that works for medians, angle bisectors, and altitudes. So since, again, you know, the ratio of the altitudes is equal to this big fraction, this big proportion, then, you know, the altitude is to altitude as the angle bisector is to the angle bisector as the median is to the median too. They're all form one big proportion if you have similar triangles. All right, let's go to the next page for a proof. So we're going to prove Theorem 7.8. So in Theorem 7.8, it says if you're given similar triangles, and we've got altitudes too, so that's just part of our given. We're given altitudes. Prove that those ratio of those altitudes, so FH is to KP as HF is to MK. So we're not going to do the full one because as soon as it's equal to the ratio of one pair of corresponding side lengths, it's going to be equal to the rest by just transitive property, since we know the triangles are similar. So we already know HF is to MK as FG is to KL. We already know all that, so we don't have to show it all. We just have to show it to one of them. And it doesn't matter which altitude we pick. We could have picked the altitude coming from vertex G and L or M and H. So since it's just chosen at random, since it's just arbitrary, right, we don't have any specific values or anything, we don't need to do it for every single pair of altitudes. So let's go ahead and go on with the proof. So I've got the given there for you. And remember that altitudes are perpendicular to the side opposite of the vertex they come from. So we're going to state that. We have to have that in our proof. So we're going to say Fj is perpendicular to Hg, and that Kp, not Kf, Kp is perpendicular to Ml. And we're going to say definition of altitude, because altitude is perpendicular to the side opposite of the vertex it comes from. So definition of altitude. So now the reason we stated that they were perpendicular is so that we can say that these are right angles. But I'm actually going to say this one's the right angle because I'm going to focus on this angle right here on this side actually. So we're going to say angle FJH is a right angle. Well, and let's say and angle KPM are right angles. And we can say definition of perpendicular, or you can say right angles theorem because we know that if two lines are perpendicular, that forms four right angles there. The intersection does. And then so angle FJH is congruent to angle KPM, and that is definitely right angles theorem because it says that all right angles are congruent. So there's no need to say the measure of the angles is 90 and use transitive. Just go right here. If you're not doing this shortcut yet, you need to get used to it. Just this right angles theorem, but you have to have those two steps there. Okay, so now we're going to focus on the fact that these are similar triangles. So we know some things. We know we've got the proportional side lengths of all the sides, corresponding sides, but we also know that corresponding angles are congruent. So I'm going to say that angle H is congruent to angle M. And there's a reason I'm choosing that specific one, because what I'm trying to show, guys, is that these two little triangles that are formed are proportional. And I could do that with these two triangles as well, because I'm going to have AA similarity. I've got this right angle, and I'll have these angles congruent also. Or you could have had G and L congruent, and then these as right angles, which are congruent, and prove that these two triangles are similar. Because as soon as we prove those triangles are similar, we're going to have proportional pieces, okay? So angle H is congruent to angle M. Our reason is that corresponding, and we cannot say definition of similar polygons because it's not in the definition of similar polygons. It's a property of similar polygons, but it's not in the definition. The definition says same shape, different size, but not necessarily the same size. So corresponding angles of similar triangles are congruent. So it's kind of like you guys were talking about maybe a CP-CTC form of for similar triangles, but we can't do that, okay? So let's mark those as congruent there. All right, so now I have that these two triangles are similar, but we have to state that. So we're going to say triangle FJH, I'm going to call it FHJ, is similar to triangle KMP, and our reason is the AA similarity postulate, because we have two pairs of corresponding angles that we know are congruent. And now because of that, we have the ratio of their corresponding side lengths forming a proportion. So we know FH is to KM as FJ is to KP as JH is to PM. We know that full proportion. But we're only going to focus on one part because look, these pieces, which are of these two triangles, the side of these two triangles, it's also the altitude of the two bigger triangles that we were focusing on in the beginning. So we want to show this. Well, we have this now because FJ and KP are both in these littler triangles. So we have FJ is to KP. Those are the altitudes of the bigger triangles, but they're also in these smaller triangles, is equal to the ratio of HF to MK, because corresponding sides of similar triangles are proportional. So we didn't have to do all of them because all we wanted to show was these two sides, so HF, MK. So we started off with similar triangles, which gave us some corresponding congruent angles that helped us prove another pair of triangles similar, so that we could get that these two pieces that were part of the original two big triangles were proportional to the other sides of the smaller triangles, which were altitudes of the bigger triangles. So that's helped us prove that theorem. So we could have also, again, gone on and just said that this is equal to all the other ratio of the side lengths of the original two triangles, just by transitive property of equality. All right, let's go ahead and go on to example 2. So in the figure, triangle LJK is similar to triangle SQR. Find the value of x and cite your reasoning. So we have those two triangles and we have this random line here, line segment. Well, what is it? You should know that they are medians. So I'm just going to say KM and RT are medians. So we know from one of the theorems, I don't remember the number, I think it's the last one, so 7.10. It doesn't matter, I don't want you to say that. But we know that the medians form a proportion with the ratio of the corresponding side lengths of the similar triangles. So that's all we're going to write for our reasoning is the abbreviation that I put for you on theorem, which is 7.10. So similar triangles have corresponding medians proportional to corresponding sides. All right, so then we can set up a proportion here. So I know that I've got this full length. We have to talk about full lengths of the sides, right? So we'll do Km is to, let's see, RT, so that's the altitudes, is equal to the ratio of any pair of corresponding sides. Well, we have to go with the pair of corresponding sides we know. So we have to do this full length here, not just a little piece. It's the full length, not these two segments it's broken up into. The full length here. So we need to do JL is to QS. And we can see that JL is going to be 2x. And we can see that this full length is going to be 10. So really that does reduce to be still x and 5. So could we have just done that? Well, yeah, because we know that JK is to QR as JL is to QS. So if you do the same thing to JL and QS, if you divide them both by 2, since this is a median, it cuts it into 2 equal pieces there, then the ratio is going to be the same. 5 is to x as 10 is to 2x, which is as QR is to JK. So that's why we could use the smaller lengths, because it's the median, and that's going to be the same since it cuts it at the same position and splits it into 2 equal pieces. So we're going to always just go with the longer length though, just to make sure that we're not making assumptions that we can't make. So let's go ahead and set up or fill in our values here. So Km is 12 and RT is 8 is equal to JL is 2x and 10. And then, yeah, hey, we can reduce it, right? So I'm just going to do cross product. So I get 120 is equal to 16x. We're going to divide each side by 16, and you get that x is equal to 7.5. And we can quickly check to see if that works. So we can just do 8 divided by 12 to make sure, see what that is. It's divide each by 4, you get 2/3, and then do 5 divided by 7.5. Well, 5 divided by 7.5 is the same as 50 divided by 75, and we know divide that by 25 is also 2/3. So the ratios work out, so that's how you can check your answer there. All right, let's go on to the last page here. So we're going to talk about the triangle angle bisector theorem. So this is specifically to do with angle bisectors in a single triangle. It's a single triangle, guys. It's not between two triangles. This is in a single triangle. Okay, I want you to put that. The other ones are all in talking about a pair of triangles that are similar. So in a single triangle, an angle bisector in a triangle separates the opposite sides, opposite side into two segments that are proportional to the lengths of the other two sides. So let's see what that means here. So I'm saying this angle bisector separates the opposite side, so BC, into segments that are proportional to the lengths of the other two sides of these sides here. So the angle bisector splits it up into BD and DC. So I'm just going to highlight them here, BD and DC. And those form a proportion with the other two sides, AB and AC. So there's a couple ways we can set up the proportion. I'm going to set it up one way. Basically, remember, these have a relationship that they're the segments that were formed by the angle bisector splitting them, not splitting them in half, but just splitting them into two segments. It's not necessarily in half. And these two relationship is that they're within the same smaller triangle that's formed. These two relationship in this smaller triangle that's formed. So the ratio is going to be, you can do it a couple different ways. You can do BD is to DC, so one of the segments is to the other segment, as another side of the triangle that goes with that first segment that you stated is to the third side of the triangle that goes with the second segment that you stated. So they go together because they share a vertex, okay? So let's go ahead and write this in words. So if AD is an angle bisector, then AD splits BC, that's your opposite side, splits BC into two segments, which is BD and DC, proportional to the lengths of the other two sides, AB and AC, respectively. So again, that's just telling you that these two go together, these two go together. So make sure you're writing that down there. So down here, if AD is an angle bisector, I'm sorry I didn't leave a lot of room here, then here's your proportion. You've got that. We're going to start with the pieces, the segments that are split. So BD is to DC as, what do you think the next one is? It's AB is to AC. All right, so again, the relationship here is they are in the same smaller triangle. They share a vertex, okay? And then these two have that same relationship. They share a vertex. They are in the same smaller triangle that's formed. And then these guys' relationship is that they are the two pieces that the angle bisector split the side BC into. And these two relationship are that they're the remaining sides of the triangle. So these are of BC and these are the other two sides of the triangle. So you really could have also set up the proportion that AB, so just this piece right here, this piece right here, AB is to BD as AC is to DC. That's also okay. This is what comes up in the theorem, but this is also a true statement. So notice that these two are these two, these two are these two. So there's lots of different ways we can write the same proportion. So you can do segment to segment, side to side, or you can do side to segment, side to segment. And just make sure you pair them up with the right corresponding part. All right, so let's do an example with this. So down here, we've got, again, it's a single triangle. We're given this single triangle that has a single angle bisector here of this vertex. So by this theorem up here that we just did, triangle angle bisector theorem, we know that we've got the ratio that this is to this as this is to this. Or you can say this is to this as this is to this. There's lots of different ways you can set it up. Based on how they set it up here, they did segment to segment. So these are the two segments that angle bisector splits this side into. So I'll do it that way. So 6 is to x as you guys fill it in. What should go next? 9 is to 15. And again, the other way you can do it is 9 is to 6 as 15 is to x. That's fine. And then any variations of these is fine too. This can be flipped. This can be flipped. You know, we can do 15x over x over here, you know, whatever, as long as the ratio is the same as our original one. All right, so then we can just solve it. It's a really simple ratio to solve. So 6 times 15, let's see, 60, 30, 90 is equal to 9 times x, 9x divided by 9. X is equal to 10. And then we can go ahead and check that by making sure it is 9/6. Well, I'll do it in the original, right? So here, so we want to make sure that 6 is to 10 as 9 is to 15. Cross products 90 equals 90. It works. All right, guys, that's it for this section. Go ahead and do the homework. Thanks for watching.